Hi, this is Ms. Schultz. So this is a video for calculus where we're going to learn how to differentiate logarithms. So let's start with some background knowledge to remind ourselves what the properties of ln of x are. So here's a graph of ln of x. So its domain, it has a vertical asymptote here at x equals 0. And so it doesn't include 0, and it only includes the positive inputs, so 0, infinity. Or you could say x must be strictly greater than 0. So I think of this like in my mind, I recall that a square root of x function looks like this, and it starts here, square root of x. So the domain isn't exactly the same because you can input 0, but both of these are similar in that they're both increasing functions, they're both concave down functions, so their look is similar, and the inputs must be positive, in this case, or 0, but you cannot have negative inputs for either of them. So the range of ln, it goes down to negative infinity, and this it never flattens out, it goes up and up and up toward positive infinity. So the range is all real numbers. Or you could say from negative infinity to infinity. All right, adjectives that describe the function. It's continuous. It's one-to-one. This is a word you don't need to know, but one-to-one means it's a function and its inverse is a function. That's fairly rare that when you take the inverse, it's also a function. Increasing. Okay, over its whole domain, strictly increasing. And any function, if it strictly increases or strictly decreases, it is going to be one-to-one. So it is concave down for the whole time. And it is positive starting from here. So from 1 until infinity, it's positive. So from 1, not including to infinity. And it's negative for this bit. So like 0 to 1. Okay, so that's to familiarize ourselves with the graph. Now let's recall its properties. So if a and b are positive numbers and n is a rational number, then the following properties are true. ln of 1. To do this, I think about the graph. If we just make a sketch of the graph, 1, 0 is our number 1 key point. So 1, 0 is a point. ln of e, 2, 3, e is right here, has an output of 1. So ln of e is 1. Also, we discovered e last year. Just to recall this, we did an activity last year with the Mr. Smarty Pants where we took f of t equals 1 over t, a rational function, which looks like this, yes, and this is a zoomed in rational function. This is just the first quadrant of a rational function. And we counted the area. Remember, each one of these boxes had 1/100th of a value. And we said, if you start at 1, where do you have to end such that you have 100 boxes? AKA the area is exactly 1. So in this orange shaded bit, the area is 1. And where do you go to? Right here, 2.718, or e. So e, that's how I know that ln of e is 1, because we designed e such that the output is 1. All right, so use the multiple choice to answer each of these. We'll come back in a second. All right, ln of ab, so the log of a product is the sum of 2 logs. And the exponent, this is the pre-calc power rule of logarithms, becomes multiplication. Because like when you raise a power to a power, that's multiplied. So n ln of a. And log of a quotient is the difference of 2 logs. This is really like the same version as the multiplication, just sort of the denominator has a -1 as the exponent that you bring in front. Okay, so those are our rules that we need to remember. Okay, example 1. This one doesn't use any of the rules, FYI. We'll apply the rules in a second, but I just want to get us started with an AP question. So you're given f of x is ln of x, okay? Which of the following is equal to f prime of e? So we're going to use the definition of a derivative to do this. I'm going to help you remember the definition of a derivative. It's that image where it looks like this, and the x plus h approaches the x plus h, approaches the x. So it's the limit as h approaches 0. That's when one point becomes infinitesimally close to the other point of f of x plus h minus f of x all over h. That is the definition of a derivative that you're going to use to solve this. And you're going to find f prime of e, where your function is ln of x. So go ahead, try to figure out which one it is. Alrighty, and the answer is D. So what's this one about? It would be ln, so the limit as h approaches 0, of ln of x plus h, and my x value is e. So e plus h minus, this would be f of x, would be ln of x, but x is e, so I'm going to write ln of e over h, and ln of e is 1, as we just talked about up here. Ln of e is 1, like this is the point e comma 1. So that's D. All right, let's use the log properties. So please rewrite each of these. Okay. All right, let's go over them. This one, so log of a single quotient is the difference of two logs. So this is ln of 3 minus ln of 8. You could simplify it more by bringing the 8 into exponents, but it wouldn't really help you. So this one, I want you to do, this one, when you do it, has 2 steps, okay? You want to use log of a quotient, but then one of the answers, one of the terms, rather, you can actually find a value for. Yeah, so try that in 2 steps. Okay, and we're back. So this would be ln of 1 minus ln of 4. So that's my first step. My second step is I can simplify this. This would be ln of 1 is 0. Again, it's that point 1 comma 0 is a point. So 0 minus ln of 4. So in other words, negative ln of 4. If I wanted to make that 2 squared, I could do some stuff. Negative 2 ln of 2. That'd be fun, but don't have to. Okay, this one, to do it, I'm going to get you started here. So like we do a lot of times in calc, we rewrite things first, and we do a lot of rewriting of roots as exponents. So if you rewrite this with the root as an exponent, be ln of 3x squared plus 1 to the half. So now what would that be? Okay, so this half goes out in front and becomes multiplication. 1/2 ln of 3x squared plus 1. And that's it. You cannot simplify this any further. Sometimes people think ln of a sum, you can make some multiplication or something or break it up somehow. No, you cannot. This is it. It's as far as we can go. Okay. This one I want you to try, do it in, it's going to be 2 steps. There's different ways to approach it, but try it in 2 steps. Okay, we're back. So I see the quotient first, so I do ln of 2x minus ln of 5, like that. And then I'm going to break this log of a product into the sum of 2 logs. So this becomes ln of 2 plus ln of x minus ln of 5. That would be a fully, neither of these is more simplified, quote unquote, they're just equivalent. Okay, so this is the Mr. Smarty Pants thing. This is our big jump from pre-calc to calc. So this is how we discover the ln function. So we found the areas starting from 1 to different points. But now, what do we know about areas underneath curves in calculus? We actually have a mathematical function that's a name for that. When we find the area, what calc thing are we actually doing? We're finding the integral. So this Smarty Pants activity actually says, so this was our definition from last year of a logarithm. A natural logarithm is the area underneath 1 over x, starting at 1. So we're going to have a more sophisticated definition where I say ln of x equals the integral from 1, I start at 1, and I go to some x value, and then of a rational function, 1 over t dt. I'll put the dt more to the side, dt, okay? 1 over t dt. All right, as a different exercise, if I took the derivative of both sides, I'm just gonna write, what is the derivative of ln of x? Like, what is the derivative of ln of x? I'm gonna take the derivative of the right. This is the fundamental theorem of calculus, case 2. The derivative and integral cancel out, and my upper limit of integration gets substituted in. Sometimes I have to use the chain rule, in this case I don't. So the derivative of ln is 1 over x. That's it. I should put a plus c here if I'm being really correct. So we just learned the integral and derivative, and we secretly learned it last year when we took the area underneath 1 over x and said that the area, we used our calculator, was the same as the ln. That was basically taking the integral by hand. All right, let's do some, so let's codify that here. The derivative of ln of absolute value of x is 1 over x. Why did I put the absolute value? So there's two different things you can do. You can, you need to have the domain be positive. So you can either put on the side comma, like x is greater than 0 every single time, or you can have any x be an input and just take the absolute value of your argument. The upshot is ln needs the absolute value. The derivative, it doesn't need to be in there anymore. Okay, this, most of the time, the argument is not going to be a simple x. So I like to teach this using the chain rule in the straight up definition. So the derivative of ln of u is 1 over u, but then you have to multiply by the derivative of the inside. So u is your inside, so you multiply by du. Okay. Yeah, so just to see this in the derivative way, instead of like the area of this becomes the y value of that, but in the derivative way, the slope of this becomes the y value here. So if you look at the slope at 1, the slope at 1 is 1. So the y value at 1 is 1. Let's look at, I don't know, 4. The slope at 4, if I were to estimate it, looks like, I don't know, like a fourth, probably, a fourth. So if I go over here at 4, I should expect the y value to be a fourth. Let's see. At 4, oh my gosh, so good. Yeah, so there's the y value being about a fourth.
Kevin Gomes, please come to the welcome office. Kevin to the welcome office, thank you.
So what I'm gonna use to guide this is the derivative of ln of u being 1 over u du. So this is my u. So the derivative is of log is a rational. So 1 over u, 2x, times the derivative of my inside, du. What's the derivative of 2x? It is 2. Okay. We might be able to simplify that. I want to do this one together, and then we can work on the simplification of this. Okay, let's do the derivative of this. So I'm going to identify my u. Okay, 1 over u, 2x plus 1, times du. So the derivative of my inside is 2. Okay. So let's simplify these. I'm going to put that over 1. So this becomes 2 over 2x, which is 1 over x. So the derivative of ln of 2x is actually the same as ln of x. They're both 1 over x. Crazy. Crazy. Why? Let's do this one. And then, like, why would that be true? Like, why could it, like, why is this possibly the same? Oh my gosh. All right, let's see. I'm going to use, we're going to prove it right now. I'm going to rewrite ln of 2x. This is ln of a product. I'm going to rewrite it as ln of a sum, or the sum of two logs. Sorry, ln of 2 plus ln of x. So hopefully we agree that these two are equivalent, yes? That's just a rewriting. I didn't do any calculus, I just rewrote it. Now I'm going to do calculus. So the derivative, now I'm going to derive. What's the derivative of ln of 2? It is 0. So you get 0 plus ln of x. Oh my gosh. So you get 0 plus the derivative of 1 over ln of x, which is just 1 over x. But the point is, why does this constant not matter? Because when you can break it up as a sum, and ln of 2 is just a constant. It's just a number, so its derivative is 0, so it goes away. Crazy. Okay, this one does it, let's see how it simplifies. I'm gonna put this over 1, multiply the tops. So 2, multiply the bottoms, 2x plus 1. You cannot simplify this. You cannot. You cannot simplify this. Okay, so please do this one. Alrighty, let's do it together. So 1 over u times du, which would be negative 3 over negative 3x, which would be 1 over x. So super similar to this. Some of you might have rewritten it and done it in a different way and done ln of negative 3 plus ln of x. This actually isn't even value, but it's the derivative constant is 0, and then the derivative ln of x is 1 over x. All right, try this one. This is our last one, and then I shall let you go. All right, let's do it together. So 1 over u du. The derivative inside is 2x. So I'm going to simplify that by multiplying the numerators times each other and the denominators times each other. So that is it. That is those are some intro examples of the derivative of natural logarithm. Thanks. Bye.